Okay, let's get started. All right, so you should have watched the Desmos talking about polynomial functions, right? And how do we define a polynomial function? Basically, a variable raised to what type of exponents? Positive integer exponents, right? Positive integer exponents. Because if I had a fractional exponent, that would be like a cube root, square root, something like that. So positive integers. What type of functions do I have two that we look at, right? Two polynomial functions that we tend to talk about when we think of their end behaviors. Even and odd, that's right. Even and odd polynomials. And what does the end behavior look like for even functions? Goalposts, right? Goalposts for even functions. Okay, so they're going to both go in the same direction. They're both going to infinity, either positive infinity, or they would go to negative infinity, right? What do odd functions look like? Like an Egyptian, right? Okay, all right, so that's right, polynomial functions and their end behavior. So we are going to finish talking now about some more characteristics of our polynomials. And all of this is leading us to talk about the characteristics, the roots, the multiplicity, and stuff like that. Okay, so when we think about our polynomials, we want to talk about their roots. Now, we can have, when we talk about roots of a polynomial or roots of a function, I should say, that's typically where we have the function crossing the x-axis, all right? So here I have a function, right? I have this squirrely function here. This function that you see here that's in blue, would this be an even or an odd function?
Don't that be an odd function?
It'd be an odd function, right? Moving in opposite end behaviors here. And you can see that this particular function has 4 roots to it, right? It has 4 places it crosses the x-axis. And I would also emphasize these are real roots. Yeah, real roots, because we're only graphing on a real number line, okay, as opposed to imaginary, complex. Now, these roots that you see here are also called solutions. That's another form for it. They are also, we can write them in their factored form. Okay, so we have the zeros of the function here at the x-axis. We have the roots of the function. We have the solutions of the function. And if I have, let's say, x is equal to, I don't know, we'll say that that's the number 1. If x is equal to 1, that would be a root. It'd be a solution. It would be a 0. I can also write it in its factored form as x minus 1. Okay? So for all of these zeros or all of these roots, we can represent them in their factored form. Okay? And that's really all that we're saying here in this particular box. So let's take not that function. Yeah. All right, let's take this function here. And I want to find the roots of this polynomial. Okay, I want to find the roots of this polynomial. Now, if the function that we have here is the one that we're looking at, the roots of that polynomial says, okay, I'm going to set the functions equal to 0 and solve to find the solutions. So the 3 is a constant. We don't set it equal to 0. It would just typically divide off, right? Okay. So I can set instead each of these factors, x plus 5 is equal to 0, as well as x plus 2.
Couldn't we multiply the second binomial and then distributive property then?
So that's a good question. If I'm solving the function, I don't want to expand it out, because the way to solve a function in its easiest form is to have it factored. All right, so we would want to factor it, set the factors equal to 0, and then solve each one of those using the 0 root property. This one is already factored, which makes it easy for us. We're kind of cutting to the chase here, okay? But all functions that are already factored make it very easy for us to solve. So for each of these factors that I set equal to 0, you can see that here on the left, I've got x is equal to a -5. What am I going to do here to solve that binomial on the left?
So we had to multiply it out?
Nope. Square root it. So I'm going to apply the square root property, because the square root of a square undoes it, doesn't it? They negate each other, correct? Okay.
So we'd have to have the square root.
Yep, I took the square root in blue. So the square root of x plus 2 raised to the second power just simply gives me back x plus 2 equals to 0, or x is equal to -2. Okay. Hopefully you'll start to see that anytime I'm taking my factor there that's raised to whatever power I happen to have, when I set it equal to 0, in essence, all I'm concerned with is that portion in the middle, because every single time I'm going to raise it to, I'm going to take the square root if it was raised to the second power, the cubed root if it was raised to the third power, the fourth root, and so on. Okay, so it undoes it because I'm doing it equal to 0, so it kind of goes that way.
So where does the 3 go? Then we do that.
So the 3, does it make any sense to say 3 is equal to 0 if I were to set each of those factors equal to 0?
No.
Right, that doesn't make sense because we would technically divide that off. The 3 in this is really just the amplitude, right? Or the flattening or the compression. Isn't that what it was in our trig functions? Yeah, it's the same thing here. It's a stretch.
Just only in this case, it's basically just extra information.
Yes, it doesn't help me when I'm asking to just find the roots of the polynomial. So I have 2 roots to the polynomial. I have 2 solutions to the polynomial. I have 2 zeros to the polynomial. Okay, all of those mean the same thing. Now, let's add to that this multiplicity idea here. So when we have a root that's in a, well, if I have a root that's raised to an exponent, that multiplicity tells me some information about what's happening at that root. The multiplicity has to do with the exponent on the root, okay? So in this case, we're talking about m. If m is even, then we touch the graph at that root. If m is odd, we cross the graph at that root, okay? Even we touch, odd we cross. This is not hard to consider or to remember, because how many of y'all recognize this function right there? The one I just drew.
That's a
Right?
quadratic function.
Doesn't that look like f of x is equal to x squared?
Yes.
So it would have a root at 0, it would touch at 0, and then it would bounce back off, wouldn't it? Okay? Let's think about this one here. In its most basic form, that is what? X cubed. Notice that we have a root at 0 and we are crossing at 0. Okay, so if that helps you to kind of make that connection. We touch for even, we cross for odd.
Oh, okay.
We touch for even and we cross for odd. So coming back up here, if we were looking at our roots, and I wanted to know the problem we just worked, if I was looking at this, we know that we had roots at -5 and we have a root at -2. What are we doing at that root of -5? Are we crossing or are we touching?
We're crossing.
We're crossing because it has a multiplicity of 1, doesn't it?
Yes, ma'am.
What are we doing at x plus 2?
We're touching.
We touch. Those are also called repeated roots, the even ones. Okay? All right, so let's look at this example here. This first example says, I want to, what do I want to do? I want to find the roots, find the multiplicity, and then determine whether we cross or we touch. Okay? So, for this particular problem, and I wanted to show you this problem here because I want to highlight how we would solve this particular problem. In the previous example, it was already factored. Pretty easy to set it equal to 0 when it's already factored. So now if I want to find the roots, I need to factor it. Okay, but what do you notice? How many terms do I have here? 4. What's the strategy for solving something that has 4 terms in it?
Okay.
No, but at least you guessed. Good job. Thank you. But it's not it.
What was the question?
Quadratic only works for 3 terms.
Isn't it where you put like x plus y and then the quadratic? I don't know what the whole thing is called, but
I don't think so. Maybe.
Don't you group them?
Grouping. Were you thinking grouping?
someone.
Okay. So we're going to group, because I think maybe we're going with this in the same direction. We're going to group this. And I'm going to come in here and I'm going to just stick parentheses around the first 2. And I'm going to stick pairs and I'm going to stick parentheses around the second 2. Look what happened when I stuck a parenthesis in between 9 and that subtraction sign. I cut it off, didn't I?
So I was saying
So I-
first group minus the second group, right?
Well, I'm just grouping it right now. So
Okay.
because I put a parentheses here in between that minus sign and 9, I now need to change the sign on the inside. Let's think about that. I got to be able to undo it to get back what I started, right? So I would distribute the negative back in. All right. Now, when we group, the idea behind grouping is let's just look at the first set of parentheses here, those first 2 numbers. Is there a GCF that I can factor out of those first 2 sets?
X,
that.
X squared, right?
X squared. So I'm going to factor x squared out. That leaves me with x plus 5. Bring your minus sign down. Now, this is the idea behind grouping, is that I want to see in that second set of parentheses, I want it to factor with an x plus 5 left over. That's kind of a guide right there. All right, so I'm looking, hold on, Javi. I'm looking at this set of 2 numbers, 9x plus 45. Can I factor anything out of it?
5.
Leaving me with
X plus 5.
x plus,
No.
no. I can
Leave like
factor
9.
9 out, leaving me with x plus 5. Now, how did I know that that wasn't working out? Because I want both of these to contain the same binomial x plus 5. So that's kind of a hint that if you did not change this sign here and you ended up with x minus 5, go back and look. You did it wrong, right? That's it. You should end up with the same binomials. And now, is there a GCF in between these 2 terms?
X.
Nope.
X plus 5?
X plus 5 is common between both of those terms, right? X plus 5 is common between those 2 terms. That's a GCF. It's the same thing as what we were doing above. So we're just repeating the process. So I'm now, in essence, going to factor x plus 5 out of each of those 2 terms, leaving me with x squared minus 9. That's the grouping method. And it's a strategy when you have 4 terms. Now, can I factor that again? Yes, because x squared plus x squared minus 9 is the difference of 2 squares. So this would be the square root of the first minus the square root of the second times the square root of the first plus the square root of the second, right? It factors into that plus and minus binomial. Okay. So now I haven't answered the question. All I did was factor it. Let's set it equal to 0 and solve. Once it's factored, we're using that 0 factor property. Okay, so I have x plus 5 equals 0, x minus 3 equals 0, and x plus 3 is equal to 0. So x would be equal to -5, +3, and -3. Yeah? Okay. Now, what is the multiplicity at the root -5? What's the multiplicity? All right, so we have a multiplicity of 1 here, meaning we are going to cross or touch. What's the multiplicity on 3?
1,
We are going to cross or touch.
cross,
What's the multiplicity on -3? 1, we are going to cross. Okay? Is that what you were talking about doing, Eric?
Someone.
Yeah, that's the grouping method, and it's basically just a form of the GCF. Okay, so when we are solving for roots, we want to put it in its factored form if at all possible. Let's look at this one right here. -2x to the 4th plus 2x squared is equal to 0. I'm going to take out a 2x squared. I'm actually going to take out, so this is written in descending order, right? So we have a leading coefficient here. I typically want my leading coefficient to be positive. It's the easiest way to factor it, right? So I'm going to factor out a -2. So I have a -2x squared, leaving me with x squared minus 1 equal to 0. Now, I can set each of these factors equal to 0 if I want from here. At this point, I can set them equal to 0. So I would have -2x squared equals 0, or x squared minus 1 equal to 0. So on the left, I would divide off my -2. I would end up with x squared equals to 0, or in other words, just x is equal to 0, right? And then here at x squared minus 1, you have 2 options at this point. Okay, give me one of them.
go ahead and square root it.
Okay, add 1 to the right-hand side. Okay, that's probably what I would do. X squared is equal to 1, because that gives me a positive value, and then I could take the square root of both sides. So x has to be equal to what? And
-1.
positive and -1, right? When I take the square root of a number, I'm going to get the positive and the negative value. Could you have factored x squared minus 1 into x plus 1, x minus 1, and gotten the same values? Yes, you could have, okay? So either method works, doesn't really matter, they both gave me the same roots. One is applying what we call the square root property here, right? when I solve using the square root property, meaning I'm gonna solve it by taking the square root, and one is just factoring using the zero factor property, okay? Now let's come back to the root at 0. What's the multiplicity here? All right, so it has a multiplicity of 2, meaning I'm gonna do what there? All right, I'm gonna touch. What's the multiplicity at, for this second value?
2.
Is it?
It'd be 1 because we split it.
It would be 1 because let's go back to it in its, let's move back to this location here, right? X squared minus 1 is just raised to the first power, isn't it? Yeah. So it still has a multiplicity of 1, so we would just cross. If you had broken it down further, you can see each of those have a multiplicity of 1, so again, you get the same result, okay? All right, so we want to factor and we want to determine what the multiplicity is. Do y'all have questions on this so far?
So since it was x squared to 0, and then when you square root, that's 1 is 2 because it's x squared
Yes.
equals 0, and then with the other ones, you can split it up into x plus 1, x minus 1.
Yep.
That's why it's like multiplicity. So is there an example where we would have like x equals 0, and then that
But that would be what?
would be cross, but would that be like something like out for, I guess?
It would still just be a single crossing at 0, but it would be considered a repeated root still. Anytime you've got that. Now, the only time that's going to come into play is when we actually do our long division, and that's another story, all right?
Okay.
But ultimately, I'm just crossing or I'm just touching. Let's look at this problem and go backwards. So for this problem here, I want to create the polynomial with a function of degree 3. We didn't talk about that. Maybe we should in a minute. Who has zeros at -2, +2, and +3. So I want to create some polynomial with a function, a degree of 3, who's got these zeros in it. So we're going to take the zeros and we're going to rewrite them in their factored form. So at -2, that looks like x plus 2, doesn't it? In its factored form. At +2, that looks like x minus 2. And at +3, that looks like x minus 3. So these are the zeros, these are the roots, we were given those, and I want to put them together to create the polynomial. So we have a function that looks like x plus 2, x minus 2, x minus 3. Now I want to simplify that, in other words, expand it, right? Get rid of the parentheses. Y'all do that for me on your paper. Okay, you get x cubed minus 3x squared minus 4x plus 12. Yeah. All right, now I did that because when you are multiplying factors like this, you got to work in pairs, don't you? You can't take this x and try to multiply it here and here. You can't distribute it across those like that. So you have to simplify, and I chose to simplify the first two, right? I had to multiply, I FOILed the first two, and I got x squared minus 4, and then I multiplied those two. Okay, so you can't just take the x that's in the front and distribute it across all of these pieces. It doesn't work that way, okay? All right. So now, this was a degree 3, right? This was a third degree polynomial. How did I know it was a third degree polynomial? How do I verify that I created a third degree polynomial?
Because that's
Coefficient.
coefficient, leading coefficient.
The leading coefficient, right?
Leading coefficient of the power of 3.
Right, so in descending order, starting with the highest power, that's the one that tells me what the degree is, right? Just make sure, okay. Now, talking about end behavior again, right? We know that when we have even functions, they look like goalposts moving to infinity. So when I'm looking at this question, or when I'm looking at this notation, we do this a lot in calculus. As the function moves to, no, I'm going to read it this way. As x is moving to negative infinity, so as my x values are moving to negative infinity, the function itself, the y values are moving to positive infinity, aren't they? Okay. As the x values are moving to positive infinity, the function itself is moving to positive infinity, right? That's how we read that. Do you see that? Let's practice that again. Let's do the odd one. As x is moving to positive infinity. So if I picture all my x values here, if I picture the x-axis moving to positive infinity, all my y values are increasing, right? They're getting larger, going to positive infinity, aren't they? Okay, so as x goes to infinity, the function goes to infinity. As x goes to negative infinity, right, the function is going to negative infinity as well. It has a little bit going on here in the middle, but that's all right. The end behavior is what we're talking about. What's happening towards the end, okay, as we go off forever. Now, another characteristic of our polynomials has to do with the turning points. So even though I have an even function, right? Even though I had an even function up here that looks like goalpost, right? Or W, let's say, I've got 1, 2, 3 turning points in that function, right? I have 3 places where the function turns from negative to positive, right? Or positive to negative. Those would be turning points, okay? So when it's, and what do you notice about where are these turning points technically located at? What would you call them in the past? Like this guy right here.
The vertices.
Or not a vertex necessarily, no. Let's call it something else. Max and mins, right? Aren't those occurring at max and mins? Okay, they're technically local max and mins or relative max and mins, aren't they? Okay, we don't have to go into all that, but the turning points are occurring at where that value is the least in that section or the greatest in that section. Okay, so those are polynomials. And we have this concept that says if we have a polynomial of degree n, then the graph has at most n minus 1 turning points. So it's not going to have any more than n minus 1 turning points. It can have less than that, okay, but it won't have more than that. So let's pretend that this, how many turning points do I have here? That I'm circling in this function right there. 3. So this would be one option would be that this is a 4th degree polynomial because it has at most n minus 1 turning points, right? Okay, I went backwards on that. But if you have 3 turning points, then you're going to have a 4th degree polynomial. Okay? If you have 3 turning points, you would have a 4th degree polynomial. I could have 1 turning point and still be a 4th degree polynomial. Okay, but I'm not ever going to have any more than 3 turning points on a 4th degree polynomial. Okay? That's what that says. So here I have this guy right here. So I have a polynomial that I'm giving you, and I want to be able to take that polynomial and come up with an equation that matches it. Okay, so I want to come up with the equation for that polynomial. Okay, and that's what it says up there at the top that you can't see very well. So if this is the polynomial that we're looking at, first, let's determine what is our end behavior. What's, do what? It's an even function, right? The end behavior is both goalposts going in the same direction, right? And would we say that this would be positive even or negative even? Positive even. All right, so we're going to say that this is positive even. Okay, we just talked about this, but the next thing we're looking for are the turning points. Okay, so I have a turning point here, a turning point roughly here, and a turning point roughly there. I don't know, I mean, I didn't mark those correctly, but you can see I've got turning points, right? I have 3 turning points. So if I have 3 turning points, what's the degree of the function? A 4th degree polynomial. That's why we're looking for the turning points. Just add 1 to the turning points. Okay, let's get rid of that. Now, let's determine the roots. The roots and the multiplicity. Okay. I think most of you can see that well enough. I have a solution here. Here and here, don't I? Right? I have roots that are occurring there. I have solutions that are occurring there. I have zeros that are occurring there. And all of those are occurring at -3, -1, and a +2. So moving backwards, I know in factored form, that would be x plus 3, x plus 1, x minus 2. Do we all agree with that? Yeah? What's the multiplicity at each of those? So at -3, I have a multiplicity of 1, correct? I'm going to put that over here. Well, I don't really know technically if I have a 1 there. You're going to see that I do have a 1 there, but I just know I crossed there, right? So I have an odd multiplicity there. What about here? It's even, right? Okay, but we'll see. We'll go with the lowest numbers for right now. Okay, and then what have I got going over here at +2? I got a cross, so I'm going to have the smallest value I would have there would be a 1. Now, if I expand all of these out, I would have this variable raised to the first power times this variable raised to the second power times this variable raised to the third power, or to the first power, right? So x to the first times x squared times x to the first. What happens when I multiply x to the first, x squared, x to the first? What do I do to the exponents when I multiply their bases? So this becomes x to the fourth, doesn't it? Okay, so I only had a fourth degree polynomial, so I was able to use those smallest numbers here, which is, you know, we're not trying to make this too difficult, but that's how I didn't really know. You know, you gotta check that. Okay. Now, I have a general equation that might look something like x plus 3, x plus 1, x minus 2, correct? Okay. But I can actually make this equation a little bit more concise if I can find the actual equation. All right, now I'm missing, remember that leading coefficient? Okay, remember that leading coefficient, we're going to call it A. All right, and that leading coefficient actually tells me how compressed or how flattened out my function is, right? I can have all sorts of functions that are fourth degree polynomials that cross and do this behavior right here at the x-axis, but I don't know how much it's doing that, do I? Right? I don't really know a whole lot more. I just know it crosses here and the end behavior goes up, okay? So we want to get a little bit more technical with this, and we are going to solve an equation. We're going to solve and try to figure out what would this leading coefficient be, right? Because it's the part that affects our amplitude, okay? And what we're looking at here is if I have y is equal to some leading coefficient times my polynomial we're creating, and I want to solve for A, I'm going to look to my graph and I'm going to say, because notice the other variables that I have in there are a y and an x, yeah? Well, I can pick a point off of my graph that's represented by the x and the y, and I can plug it into the function because then that eliminates all the variables except A, all right? Now, the easiest one for us to locate, right, if there any point on this function, any point on this graph would work, okay? Because any point on the graph makes the left-hand side equal the right-hand side if I plug it into the equation. But there is one particular point that would be the easiest to use, and that is, say, this one right here. I can clearly identify that y-intercept, right, as 0, -3. So I am going to let y be equal to 0 and plug in, sorry. I'm going to let y be equal to -3 and 0 be equal to x. So we are using the point 0, -3 to solve for A. Just notice when I plug it in there, I got rid of every variable except the one I'm trying to solve for. So I have a -3 is equal to 3 times 1 times a -2 would be -6, right? So I would have -6a. Divide both sides by -6, and I find out that A is equal to -1/2. oh, excuse me, positive 1/2. Yeah. So that's 3 times 1 times a negative 2. Which is why 0, if I could use it, was a really nice number to use. So now I have the function positive 1/2 times x plus 3, x plus 1 raised to the second power, x minus 2. That's the function representing that equation. Okay, and you can do that for any equation, right? If I can come up with the general form of a function, I can actually find the actual equation if I can locate a single point and plug it in to solve for it, all right? Okay. Now let's practice sketching the graphs. All right, what I want to do first is I want to change that equation. So hold on a second, because I want to graph this other one instead. So let's graph x squared times 3x squared minus 10x plus 7. Okay. We're going to go through these steps, and although we're going to use our calculator at some point to be able to help us do this, this is going to pay off if we can kind of practice this process of sketching when we move into the to curve sketching and calculus. All right, so we're kind of practicing some of that stuff. Again, I realize that you can throw this into the graphing calculator, but it's going to help us out if we can kind of practice our process, okay, here. So in order to sketch this graph, let's first determine what the end behavior is. Okay, so we have x squared times x squared. So x squared times x squared is going to be x to the 4th. Therefore, this is an even function, right? And it's positive, so we're going in the same direction. Now let's find the roots of the function. How do we find the roots of the function?
Factor out to where we can get it.
Set it equal to 0 and solve. Okay, set it equal to 0 and solve. So I have x squared times 3x squared minus 10x plus 7 is equal to 0. X squared equals 0. That's pretty easy. Let's see if we can factor 3x squared minus 10x plus 7 any further. The first is prime, the last is prime, so this should factor using trial and error. I mean, it's not hard to practice it that way. So 3x minus 7x minus 1. Did I do it right? How are you going to know if I did it right? What are you going to check? I just want to check. I just want to check the outer and the inner terms, don't I? We all know 3 times 1 is 3. We all know 7 times 1 is 7. But did I put them in the right order?
No.
Did I not? I've got
Because you got
negative 3x
Oh, minus 7x. Okay, yeah, you got it.
plus the 7x is a negative 10x, right? Okay, so I did put it in the right order. That's equal to 0. So here I can take the square root of both sides, right? And I find out that x is equal to 0 here. I have 3x minus 7 is equal to 0. 3x is equal to 7. Or x is equal to 7/3. And then x minus 1 or x is equal to 1. So those are the roots. Now let's look at their multiplicity. At 0, what do we do? What is our multiplicity?
It's even.
Okay, at 0, we know for a fact the multiplicity is 2. And so that would be even, and therefore we're doing what? Touching or crossing? All right. At 7/3, what's the multiplicity?
1.
1, and do we cross or touch? At 1, what am I doing? What's the multiplicity? 1, and do we cross or touch?
Cross.
Okay, so we've got the multiplicity part. Now we're going to test some points to kind of determine, we know what's going on at the x-axis, right? We know that we're crossing or we're touching, but we're going to test some points to actually see where I'm at around those intercepts, around those roots. Okay, so let's draw our x-axis. And I have an intercept, or I have a root at 0, I have a root at 1, and I have another root at 7/3, correct? So I'm going to write my roots down, I'm going to write my zeros down as if I was writing them on a number line. So they need to go in order. This is your test points. Okay, and what I want to do here is, I know that to the left of 0, right? To the left of 0, my function is going to negative infinity, right? So I'm thinking of any values from negative infinity to 0. And on the right over here, I'm looking at values from 7/3 to infinity. And really all I'm interested in are some points that are right around these roots. So we're going to just pick points to the left of 0. So I'm going to pick a number to the left of 0. How about -1? That's a pretty easy one, right? Okay, so I've got -1. I'm going to pick a number between 0 and 1. I'm picking numbers between. I'm not picking numbers on. I'm going to pick a number between 0 and 1. How about 1/2?
Yeah.
Okay. Let's pick a number. Now 7/3 would be what? 2 1/3?
That's good.
So let's pick a number between 1 and 2 1/3.
2.
Okay, 2. Now I'm going to pick a number to the right of 2 1/3.
2.5.
How about 3? If I can avoid the fractions, let's do it. Okay. And what I'm going to do is, so I'm going to evaluate the function at each of these spots. Before we do that, I'm going to set it up for you. F of 2, F of 3, okay? So I am picking points around the roots, and I want to know whether my function is, what the value of my function is. Now we're going to need to do this anyway, so y'all get your calculators out. And I want us to set up our calculator in a particular way to make this go faster. Okay, so I want you all to go to let's see, second window. And I want you to arrow down until you get to the independent, and I want you to arrow over to ask. I want you to hit enter, And I want you to arrow back over and make sure that it's highlighted. Okay? Did everybody do that? Yeah, so we are forcing our calculator, so independent would be our independent variable, and obviously dependent would be the dependent variable, and what we're doing is we're making our table of values wait on us to enter, so it's asking us to enter the value for X, and it's gonna spit out the value for Y, because I want very specifically to talk about values. I don't wanna have to scroll through a table of values, right? I want to ask it and answer it. Now, what we want to do now is let's go back to our y equals. And I'm going to put this function on our y equals. Now, the function we started with was x squared times 3x squared minus 10x. Because we're still using our calculators for this, but we are practicing other stuff as well. X squared times 3x squared minus 10x plus 7. Okay? Everybody get that put in? Even on your Desmos calculators? Okay? All right. So now did everybody get that put in? Yeah, shake your heads if you're done. All right. So now let's go to second graph. Is yours empty? Is your table empty? Yeah, okay. So if you've put numbers in before, like I have, then it will, it'll just have those numbers in. Go back to our paper that we were looking at, and we said that we want to test the x value of -1, right? So I'm going to enter -1 into the calculator, and it's going to evaluate my function for -1, the one we just put in at y1. And now I'm going to evaluate at 1/2. And I'm going to evaluate at 2. And I'm going to evaluate at 3. Okay. So this is allowing me to, again, ask my calculator for the values that I'm interested in, not the values that the table is just producing. Okay, so I'm being very specific in that. And what we want to do is we want to write down on our paper, I want to know, was the function positive or negative at -1? So let's just write a plus sign down there. Is the function positive or negative at 1/2? Positive. Is it positive or negative at 2? Write that down. And is it positive or negative at 3? Okay. So we had negative, or excuse me, we had positive on the left. So we have positive, positive, negative, and positive. What we found is that this here, 0 is our root, correct? And we know that we are touching somewhere at that root. I mean, we are touching at that root, right? What we found when we tested to the left of that root is that the function itself is going to have positive values. So it's going to be somewhere above 0, the x-axis. That's at 0. We know that from 0 to 1, we are also going to be above the x-axis, right? Okay, because we have positive values in that test area. We know that at 7/3, so I'm going to put the number 2 here, and I'm going to put the number 3 here. We know at 7/3, oh, I skipped one, I apologize. We had a root at 1, did we not? Okay, and we are negative, right? So I'm going to be somewhere down here in between my root at 1 and my root at 7/3. And then on the right of 7/3 will be positive again, okay? Now what does this look like? Let's go back to our graph, and I want to pull up, let's go back to our calculator, and I want to graph this. I'm gonna go here and I graphed it. So I just went back to my calculator and I hit graph. Now I rearranged my window really fast. I clicked on standard window. So I went to zoom 6 if your window was out of whack. Okay. And here we have the function. So when I'm graphing this function on my paper, I want to know where the turning points are located at, okay? But notice on my equation, on my function here, we said at 0, the function is on the left and the right, the function is going to be above the x-axis, isn't it? Here we have a root at 1, so we're crossing the x-axis at 1. And then we cross the x-axis again at 7/3. And what do you notice there? That the function itself is below the x-axis, right? Which is that negative value. And then to the right of 7/3, we are now above the x-axis again. So that's what our test value is allowing us to visualize. And we will get very, very familiar with this in calculus when we do our curve sketching. But it's nice to kind of know what we're talking about in about another 4 weeks, okay? So to sketch this now on your paper, let's determine what are the actual ordered pairs for these turning points. I want to know what the max and the min values are, okay, to 1 decimal place. So to find the, let's find the maximum here that's occurring between 0 and 1. So if you don't remember how to do that, we're going to go to second trace, and I want to find maximum. My arrow is flashing. I'm going to scoot over just a little bit because it defaulted to, I think, 0. Now you have to tell the left boundary. So I want to mark it on the left side of the max. So I'm going to hit enter somewhere up to the left of that. I'm going to arrow over past my maximum and mark my right boundary somewhere. It asks me for a guess. I don't know. That's kind of the point of the calculator. And I hit enter one more time. And I find out that the maximum point, right, the maximum value between those bounds that we found was at 0.6 and 0.75, we'll call it. Do you all get those values? You should. Okay. Now go in and find the minimum. It's 3 buttons. It's 3 steps. Okay. Do you get 1.87 and negative 4.2, something like that for the minimum value? Yeah? Okay. So when I want to sketch this, I'm going to put here, what did we say that max was occurring at? 0.6 and 0.75? Yeah? Okay. So I'm going to label that as 0.6, 0.75 on my graph. I'm going to put a point there representing 0.6 and 0.75. I'm going to put a point representing the other value. What was that one at? What did we say? 1.87 and negative, I'm going to call it 1.87 and negative 4.2. Is that close enough? Is that what y'all have roughly? And now I'm going to sketch it. So crossing through the x-intercepts, crossing through the turning points, end behavior. That's what I'm looking for on a test. Okay, so we're still gonna let the calculator help us out here, but I want us to walk through the process of it, okay? And clearly label your turning points for me, the ordered pair of your turning points. You notice that I didn't have to get really, I didn't have to draw this thing to scale. I just kind of stuck on there my turning points. So don't think you have to be too dramatic about it. Now, what is the domain of this function?
Negative to positive infinity.
Okay, so the domain would be from negative to positive infinity. What's the range of this function?
X is, y is greater than negative 4.2.
So greater than or equal to, right? I can include the negative 4.2. So we have a bracket of negative 4.2 up to infinity. Parentheses, right? You remember the difference between brackets and parentheses for domains and ranges? Do y'all remember that? Brackets are for inclusion, parentheses are not. Now let's talk about where the function is increasing. When we talk about where the function is increasing, we're talking about where the y values are increasing, right? Okay.
Aren't they increasing from 0 to negative infinity to 0?
Nope, it's increasing from 0 to 0.6, right? The function itself is increasing. Those y values are increasing till x is equal to 0.6, right? Okay. Then the function is increasing again from 1.87 to infinity, right? So that's where the function is increasing, and we refer to increasing and decreasing as just open parentheses. So I would say from 0 to 0.6, the function is increasing. And then from 1.87 to infinity, it is also increasing.
Wouldn't you like a little logo?
We don't have to. Now, decreasing, where is the function decreasing? The function, even though this arrow implies it, the end behavior goes off that way, right? As x is getting smaller, the function is actually decreasing, okay? So as x is getting smaller, the function, read it from left to right. When we're talking about increasing versus decreasing, read the graph from the left to the right, okay? So the function itself is decreasing from negative infinity to 0. And again, from 0.6 to 1.87. Okay. So when we're thinking about increasing and decreasing, we're reading the graph from the left to the right. We're talking about where the function y is decreasing as technically x is increasing. Let's practice that one more time. Are there questions on it so far? Okay, so these are the steps that we're going to go through to sketch it on our homework as well as on a test for me. So the next one that I want to talk about is this function here. Negative 9 half x plus 6x squared minus 2x cubed. So talking about the end behavior, right? Maybe it would be helpful for us to rearrange the function first. let's say f of x is equal to negative 2x cubed plus 6x squared minus 9/2 x. If I write it in descending order. So what's the end behavior here?
Isn't it gonna,
Is this even or odd?
it's odd,
Okay, so this is an odd function. But there's a negative sign for the leading coefficient, correct?
so it's gonna flip, isn't it?
Yes, so we are going to move in opposite directions, but on the left, we're going to increase, right? We're going to go to positive infinity, and on the right, we'll go to negative infinity. Now, what do we want to do? Find the roots. How do I do that? Okay, I'm going to set it equal to 0, and I'm going to solve. So I would have this thing equal to 0. Well, there's a fraction here. So let's factor that fraction out. Okay, so I'm going to factor out a negative 1/2 x. When I factor that out, that's like dividing, right? Factoring is like dividing. So I am dividing 2 by 1/2, which is multiplying it, right? So if I divide by 1/2, I'm multiplying by 2, correct? All right. So 2 times 2 would be 4x squared. 2 times 6 would be 12x. And then the whole point of factoring out the 1/2 is to get rid of that.
2.
Yeah, so if I multiply 9/2 by 2, I just get 9,
9.
correct?
Would be negative 12 actually. Yeah, we need to change.
Yes, it would, thank you. So I have 4x squared minus 12x minus 9. Challenge yourself to multiply that 1/2 back in there, and do you get what we started with? You should, okay? We should get the same thing. And I factored the negative out because I want my leading term to be positive when I try to factor that trinomial. Yes, sir?
Does the 9 become positive too?
Yes, it does. Thank y'all for paying attention to the signs. Okay. So I have a trinomial here. What do you happen to recognize? Okay, so I have a trinomial. The first term is a perfect square and the last term is a
So can
perfect
we just
square.
like get two binomials, make out like the perfect square formula?
Well, what do I notice about this? The first term is a perfect square and the last term is a perfect square,
Square.
correct?
Yes, ma'am.
So this does factor into the square root of the first minus the square root of the second squared. Negative 1/2 x was out there in the front. And 0. That's that binomial we like to use, right? So the square the first, double the product, square the last, and we get what we started with, right? 4x squared negative 6 times 2 would be negative 12x, and then the last term squared would be 9. So that's a perfect square trinomial when we're looking at it right here. First term is a perfect square, last term is a perfect square, and the middle is actually twice the square root of the blah, 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 right? That's what it was. So now we have this, okay? Set those equal to 0.
What, what about that square?
So I can write it as a square here.
Oh,
And then
so
if I take the square
square
root of
root.
it, since the other side is already 0, it just cancels that part out. But what's the multiplicity now at this root of 0?
1
And so we're going to do what there?
cross.
What's the multiplicity at 3/2?
2.
2, so we're going to do what?
touch.
So I have my test points, which is basically a zoomed in picture of my x-axis. So I've got 0 for a root and 3/2 for a root. So let's pick a number to the left of 0. What if I pick -2? Am I still going to end up with a value that allows me to, all I want to know is it positive or negative? That's all I'm looking for. Is it positive or negative? So you could pick any number to the left of 0. We could all pick different numbers, but we should come out with the same result. Okay. So we said -1. Is that what y'all said? Yeah. And what about in between 0 and 1.5? Yeah, that's a good one. What about to the right of 1.5? And how are we going to find this? Because we have to graph it anyway, right? So we're going to come in and we're going to put the function in the graphing calculator. So we had 9/2 x, -9/2 x. With -9/2 x plus 6x squared minus 2x cubed. And I'm going to go to my table. And at -1, we're positive. At +1, we're negative. And at +2, we're negative. So we went positive, negative, negative, correct? Okay. So now we want to graph it. All right, and now we're going to sketch it. So find your minimum and your maximum. Really, we just have one to find, I think. Did you find your minimum at 1/2 -1? Yes? Okay. We know the function is crossing at 0, comes down to our turning point, comes up, touches at 3/2, and travels on down. So again, if you're thinking of those test points, to the left of 0, the function itself is positive. To the right of 0, the function itself is negative, right? That's clearly seen by the graph that we're showing. We know that we're crossing at 0 and touching at 3/2, and we had our end behaviors moving in the opposite direction. What's the domain of this function? Negative to positive infinity? What's the range of this function? Negative to positive infinity, right? Where is the function increasing?
From, from 1/2, from -1 to 1/2. No,
It's the x coordinate, so it'd be from 1/2 to 3/2, correct? That's where we're increasing. We're decreasing from negative infinity to 1/2 and 3/2 to infinity. All right, questions on that? No, none? All right, the last thing that we're gonna do together then is practice a regression. So if you're using Desmos for your calculator, that's a little bit more challenging for a regression. You need to look up the instructions. They're out there. Google it, regression on Desmos, all right? Now, if you're using the calculator like the rest of us, then we're gonna do it using our regular calculator. So remember, a regression is a model that fits the data. It's an equation that models the data. So here we have a table that represents the cost of printing textbooks. So textbooks, right? The number of textbooks is going to be our independent variable. The cost is going to be dependent, right? Because the number that you print, or the cost depends on the number that you print. So L1 is generally our independent variable. L2 is our dependent variable. And we want to create a scatter plot representative of this data. So we're going to put in our calculator this data that you see right there. So everybody put L1 and L2 in your calculators. You remember how to get there? Okay, let me show you. Sorry. Yeah, sorry. Okay, let's go here. I'm going to go stat, edit. Remember, we had lists, we have stuff here. So I'm just going to arrow up and hit clear and then hit enter. Arrow up, hit clear, and then hit enter. L1 is independent, L2 is dependent. So there's your list. Okay, did everybody get that? I can walk around and help you if you couldn't find that again. Isaiah, put this in a table for me.
How many do you put all the values in there?
Put every value in for the L1 and every value in for L2. I didn't bring mine, otherwise I'd let you borrow it. Do you all have those entered in? Okay, let me enter it. Okay, so we've got to go to our y equals, clear out the function that we had there. Arrow up and turn your plot on. And arrow back down. Now let's see if I can go to Zoom 9. Oh, good, that worked pretty well. Yay, I don't have to adjust my window. So I hit Zoom 9 for Zoom stat, and it threw up my data there in a window that I could see it in, right? I didn't have to adjust the window. And I've got kind of what it looks like might be a curve, right? Looks like it might be a cubic function. Would you agree? Ish? Okay. All right. So now let's go back to stat, arrow over to calc, and you can see option 6 says cubic regression. I think, Isaiah, it's y1 tilde, like a, like a single tilde thingy. And then it might be like ax1 cubed plus bx1.
I'll look it up on the.
How did you just Zoom, option 9. Did you see that? Zoom, option 9. And then did it work for you? Sam, did you
I
get
have
it?
to clear the last.
Yes.
Yeah. Okay. Yes, you can't have an equation on y1. So now if I come up with an equation, I want to store the equation on y1, right? That's why I cleared it off of there in the first place. So I'm going to store my regression using alpha trace. Yeah, alpha trace. Choose option number 1 because that's where I want to store it.
Why are we doing cubic bread?
And now I got my equation right there, right? So ax cubed plus bx squared plus cx plus d. Each one of those variables, right, or each one of those constants is given to you right there. So you can come up with the equation using the values that you see there, right? Yeah, do we get that?
What did you do to get the store ready?
Yeah.
All right, so I went to stat.
I got all the way up to the cube regression part. It's just, I need to insert something for the store. Maybe, I don't know. What to do.
Alpha trace. Did it give you the Y1 menu? Did it give you? Jonathan?
Yeah.
Okay, we good? Did we get it all stored wherever it was at? Now let's go to graph and see. Oh yeah, that's pretty good, right? Lines up pretty good right in there? Yeah? Okay, and what if I wanted to know, based on that information, I wanted to predict the cost of printing 22,000 textbooks, right? I want to predict the cost. So in other words, I want to predict what the function is going to be when I print 22,000 textbooks, or 22, because our values were in thousands, they were by thousands. Now I can actually use my calculator to do this really fast. I can go, let's see, second calc. So I can either go to the table that we already had set up, or if I only want to know one number, I can choose value. Notice that here, the calculator's sitting here waiting on me again, saying, well, what do you want for the value of x to be? And I want 22. And it evaluated the function that I threw on y1, right? It evaluated the function at 22. So it should be 176, probably thousand, I would imagine. Costs in thousands of dollars. Okay, so you could have done this using second calc. Or I could have gone to the table, typed in 22, and I would have gotten the same thing, right? Because the table was waiting on me to enter the value as well. All right. So regressions, I can come around and I can help you with those as we finish up here. Does anybody have any questions over what we were looking at so far today?
No, man. Honestly, a little easier than we've been looking at.
Yep, polynomials are usually pretty easy. Okay. Okay, I'm gonna change this one. I want that to be. Okay, so we have a little bit of time left for you to practice the work that we've done. And basically, question number 3 is just, I want you to sketch it using the same methods that we were doing in class, whether that was 5 steps or not, okay? Show me your little light. So you have to turn it to the plot on. And arrow back in. And now you know it's highlighted, okay? Go to Zoom. We just got a plot.
Okay.
Zoom stack.
Yeah. That's what it is. Very expensive. My sister, an old one.
Hello?
10 years old. Yeah.
Yeah. Now, go, yeah, Zoom, stack. Okay, and then now it's stack. Arrow over to top. Use the one that you chose. And we're gonna store it directly. So we have alpha, alpha trace. You don't remember it. You can keep hitting the button here and figure out. Yeah.
So,
So here's the equation. And so I go back to here, that's where it's at. So we could allocate rounding, right, which is what's nice. We're not too much around.
wait, we didn't know what we got.
What?
Like this.
So the question that. Right, so you can do it with okay. The multiplicity comes from if the factor four. Exponent factor the original problem. The original problem tells you the degree of the whole thing. So I know 10 by here. The multiplicity comes from the factor.
So well, I know that, but so like which is just
Yeah.
it goes
Well,
around.
you can zoom.
Yes. I don't know if I'm gonna choose.
Just go here to the here,
And
and you can adjust the X
Okay.
and Y axis. You just have to remember, they're all like this. You can do a sign regression. This is how you do really good.
I thought it was like slow. So
So, so 22. So I think if you hit this gear right here,
like what were we saying?
well, we created a model and then we wanted to say, okay, well, if this is the model representing, the cost model. If this is the model, what would the cost be if I printed 22,000? So 22 for X. So then you could, it's a little harder here because you can't click any of this. Normally you can take an equation. So I guess you could take these components here to form the equation, and then plug in X, or you could just scroll through until you got to 22. Oh, looky there, that was clever. The intersection. Yeah, that'd be fast. So it's telling you that for 22,000 books, according to the model, the cost would be 176,000 or something.
So on this one, we would just, you put this cube here, that would just make cube root, right?
Yep.
Okay. So I did do it right.
Going back to.
Wait, we're only doing. Yeah.
Yeah.
Well, I'm on.
Don't make it harder.
I thought we were Japanese.
Because you've set it equal to 0. If you take the square root of both sides. Here's the square root. It's just a pattern. You have a question or any other? I would not expand anything.
Well, I tried to see.
Oh, so it's gonna be-
If you're solving something, you want it in backward form. That's where we want things to be.
So my question is, how does that get-
In other words, your minimum is where, right there at that point, there is no,
That you just check your answer.
it's the intercept, right? There is a solution, that would be your.
Don't use the
So we find that after we find general function.
Isaiah,
So I
can you
can
bring your
find this
computer over here for just a
Yeah.
second?
Right.
So if you're gonna use your calculator, if you're gonna use that,
I've been using this.
I was gonna say, you did it.
You need
Yeah.
to know.
You just have to know the form in order, the rule form,
Yeah.
to just show.
Plug that in.
Yeah.
So I plugged in
That's where I'm at right now.
cube formula.
What is-
Y
Like,
equals,
like
I was
basically-
watching you push buttons
right, all
fast
that.
on your calculator the other day, and I saw it. You were
Gave me-
easily able to enter a fraction.
Just give me
So
one.
my son, I just bought him this one, and I think
And
this is
then
new, that right there is
Yeah, that's
new.
actually, the way it used.
So I showed him.
Right here.
Yes.
Mom did something, side.
Yeah, that's
So, so basically it's all.
Yeah, that's what he said.
Yeah.
I just, like, once I noticed that was there, I was like,
Oh,
I was so happy.
I know it.
Yeah, and then you do like, I got like one.
Yeah.
One.
Yeah, that's it. So we got
Yeah,
three
but you want
degrees.
to. There's only two.
Yep.
It's not gonna
Going
work.
back to the baby step.
It doesn't say. Well, that's A. And B, -1.
I didn't even know we could do that.
Yeah, what is it?
Yeah.
Oh.
We got number two.
That's a 3 up there, not a 5.
Yeah, that looks nice.
But
I mean,
it's gonna still give you, it just changes some things, right? Hold on.
Sure.
so will this be the whole function for 2A?
So x plus 1 is
All right,
minus
bro.
1.
You're good.
minus 3.
So,
Yeah, I think that's
I
right.
put
But
in
that would be the whole answer.
table first.
For A?
But you don't do that? Yeah.
I was just making-
And then
Thank you.
Uh-huh.
on the second part, I just. So I did Y1. And I just.
Oh, so it's a max or a min, right?
So
So
that's gonna be.
that,
A,
that
uh,
hump right there would
A,
be the maximum point, and that down there would be the min. So I'm gonna do second trace
Right.
and choose, let's do max. Now it defaults, so it's gonna give you your cursor somewhere, so you need to move to the left a little bit,
Where,
don't be shy.
where,
Okay, that's good, and that, hit enter, that's your left boundary. Now arrow over to the opposite side to get your right boundary. Hit enter.
Oh,
And again for a guess,
Not this.
A.
there it is. See, it's right there. And then you'll have to do it again when you choose the minimum.
Well, no, for a second, I thought you were continuing, and then you were like. No, it's.
Thank you, Isaiah, for teaching that.
Yeah.
We're not leaving it there.
No, I'm not asking for that. I
So
just-
so just leave it like that.
Yeah.
Oh, that's why. Oh, yeah, and then it works. And then once you have that, that'll give you your regression thing.
So the first question is real simple.
And that'll give you. Yeah. Yeah.
So is this the correct polynomial for A on number 2?
Cube minus 3x squared minus x plus 3.
Yes.
Wait, so no, one's 1/3.
Are you doing that problem? Oh, well.
Started with exactly. Done them all. Number 3? Yeah, okay.
There's no other. If you said it's zero.
Expand it,
Did you?
get rid of the parentheses.
Yes.
Yes.
No, but then when you try to. I don't. So you do a 3.
Yeah.
I see that.
Thank you. So what he says is that I have zeros at, okay, so -1 is gonna have a multiplicity of 1. At -3, I have a multiplicity of 2. So form it, nope. I don't know, at 3, you have a multiplicity of 2. So take it and rewrite it in its factor form and then stick the multiplicity on top. So when they're already factored, it's super easy. So as y'all are finishing up,
Professor, I have another question.
just a minute, as y'all are finishing up, when we come back to class on tomorrow, right? When we see each other tomorrow, we're going to talk about solving polynomials that are not factored. So you can see that when they're factored, it's pretty easy. So how do I solve polynomials that are basically high, that I can't factor normally? Okay, that's why there'll be a Desmos lesson tonight to remind you how to divide polynomials. All right, and maybe one on synthetic division if I find it, but otherwise we're going to be doing that in class anyway. So we're going to be dividing our polynomials tomorrow when we get into class so that we can break it down into its factored form as a product of its factors, because you can see that when we have factors, it's super easy to identify roots and multiplicity and end behavior. All of that stuff's pretty darn easy. Okay? So be prepared for that.
So.
So I'm not understanding this. If we have -1 with the multiplicity of 1 and then 3 with the multiplicity of 2, how are we going to get the degree 3 then?
Well, so how would I rewrite this in its factored form?
X equals X plus 1.
With a multiplicity of 1 would have what on its parentheses? Would have 1 on its
Yeah.
exponent. It would have what?
It would have just more.
This one.
Okay. How would I rewrite this in its factored form?
X minus 6 squared.
X minus 3 is the
Parentheses.
second power, right? So I would have an x times an x squared gives me an x cubed.
Also, we don't have to worry about like, putting it all up. Honestly,
Well, you need to rewrite it in its factored form and then expand it.
like my
like
thought
get rid of
process
it.
was like, I put both of those under a big parentheses with a cube.
No. No. It's telling you the ultimate degree.
Everybody just melted.
So.
Well, no, because 2a is only a third degree polynomial, so that would be x times x squared. So each of these is just to the first power.
Yeah.
But on the second one, we're getting a little bit more specific. The differences between
I
the two.
was
If you look-
thinking they were together.
It's whatever.
Okay.
They're two different.
I got it, but we don't know what else.
And behavior, we're just trying to determine whether or not it's an even function or not. When you're
-4, 0,
Is that part you don't know?
That's the thing that I got.
I think that's just counting all things one, yes. If I multiply x times x squared, I get x to the fifth. So in other words, if I were to expand the whole thing out, the leading variable would be raised to the fifth power.
Yeah, that's what I'm
That's the one
doing.
from the-
That's what I'm showing
Okay.
you.
No, multiplicity is different. Propensity had to do with touching the cross. Oh, yes, okay. Okay, so
If
this is
the
x
squared was
fifth,
inside,
positive,
then you do that.
right?
Keep it back.
So- odd functions. or those in there,
Anyways, it-
Negative authorities to the left.
I gotta plug in the function, all right?
That's what we're just trying to identify. Negative infinity, positives.
I don't know what you're trying to tell me.
I didn't even write it. All right,
It's, hold on.
how you doing? You done? And you only have 3 minutes left, so I guess you can keep working.
For number,
Right?
for number 2, did we take those factor forms when we expanded?
Expand it. Get rid of the zeros. Yeah, that's what you got. So I want you to expand it. So I want you all to practice.
Which, I mean, I guess it is.
Get rid of the
It's
front,
I just need, like,
parentheses.
That's good.
So multiply these two guys together.
I'm never with you.
Or no.
I see that it crosses.
This would imply x minus 1 times x minus 1.
Oh, wait.
So
negative,
this
positive.
should be,
Oh, wait, I don't even do
these
that.
are
Oh, it's
quantities,
negative,
right?
positive, positive.
Some difference, so it would be x squared minus 1 squared, right?
Maximum.
So you'd have a binomial at that point. and you multiply
So,
You're not gonna.
Now you grab it. That's what it's like.
Oh, yeah.
I already did.
So. You got that.
Just not the end.
yeah, just.
Exactly. Mhm. And then you refactor.
All right, well, remember.
So what I would encourage you to do is make a sentence,
Oh, you're sorting back.
Right. So it's just.
That-
Yeah, I see.
You have it.
Only differences.
So if you put decimals on your notes, then using the half. Forget your calculation. That's what I would encourage you to do. I would have a backup. Yeah. Well, that's 2A, right? 2A.
Oh, I had to fix that one.
Yeah.
Right? Okay, then that can't be.
It's
Yeah,
positive scale, right?
Get rid of that too,
Yeah.
because that would imply x squared times x.
Oh, yeah. And you gotta find the next one.
So that can't be two, it's only a third degree polynomial.
So this one in for 2B.
No. All right, let me just throw this up there and then you can go. Here are the answers to the first two. So when you expanded
Oh.
number 2, you should have got an x squared minus 3x squared minus x plus 3. And then for the B part, x cubed minus 5x squared plus 3x plus 9. You'll need to practice those, okay? Your foiling skills, your multiplication skills. Okay, you just repeatedly multiply. All right, I'll see you back here tomorrow.
Yeah.